In our previous lesson, we began to look at ways to solve quadratic equations by discussing some different factoring techniques. In today's lesson, I want to talk about another tool for solving quadratic equations, square roots. Before we jump right into the examples of solving quadratic equations with square roots, I'd like to make sure that you and I are on the same page when it comes to square roots. So, really quickly, let's do a couple of square root examples. Of course, it's easier to see how to do some of these examples if you know some of the perfect square facts, like 1 squared equals 1, and 2 squared equals 4, 3 squared equals 9, 4 squared equals 16, and so on. In fact, I would suggest that you memorize these from 1 squared up to 12 squared if you haven't already done so. Okay, let's look at our first example then of just simplifying some square roots before we actually get to solving quadratic equations using square roots. So here's the example. Simplify square root of 45. Okay, this actually goes pretty quickly as long as we know some rules related to square roots. So let me march through this one step at a time to make sure that we see how to do it. Square root of 45 equals the square root of 9 times 5. You're always allowed underneath the square root symbol to factor the number that's there. So I'm allowed to have 9 times 5 underneath that square root symbol. And the square root of 9 times 5 is the same as square root of 9 times square root of 5. In other words, I can take the square root of a product and make it into the product of 2 square roots. So I've literally split square root of 9 times 5 into the square root of 9 times the square root of 5. That's perfectly legal. And once I've done that, I can start to work on each of those 2 square roots separately. In the case of square root of 9, I know that that's equal to 3. And in the case of square root of 5, I can't really do much. So this now simplifies to 3 times square root of 5. And in fact, that can't be simplified any further. So that's my final answer. Okay, so I've just used a very important fact that I'm just going to repeat again. I'm always allowed to split the square root of a product, or 2 things being multiplied, into the product of 2 square roots. It turns out that the same is true of quotients, or 2 numbers being divided by one another. For example, the square root of 8/3 is the same as the square root of 8 divided by square root of 3. So I can do it with products. I can split square roots of products. I can also split the square root of a quotient or the square root of a fraction into 2 square roots. But it's important that we remember that such a rule is not true for sums or differences. For example, it is not true that the square root of 9 plus 7 is the same as the square root of 9 plus the square root of 7. And it's also not true that the square root of 9 minus 7 is the same as the square root of 9 minus the square root of 7. These are traps that I've seen numerous college students fall into all the time. I've been teaching for a long time, and I watch those 2 errors show up all the time. So please avoid them. You can split square roots when things are multiplied together, and you can split square roots when you have a fraction, but you cannot split square roots when the 2 pieces are either being added or subtracted. Okay, so now let me suggest that you try simplifying a square root on your own. So here's one. Simplify the negative of square root of 81 divided by 49. Well, how'd you do? Well, let's walk through it together and see. We know from what I just said that we can break this problem into 2 separate square roots and rewrite negative square root of 81 over 49 as negative square root of 81 divided by square root of 49. So far, so good. Now, if you know some facts about squares, you know that 81 is 9 squared and 49 is 7 squared. I picked those 2 numbers pretty carefully. And that means that our new fraction is actually the same as negative 9 divided by 7. You can't get that any simpler, and so that's the final answer here. Now, let me mention a couple other facts about square roots while we're here, just to make sure again that we're on the same page. First, it's very important that we understand that the square root of 49 is positive 7, not plus or minus 7. I've known some students who believe that the square root of 49 is plus or minus 7, and that's not correct. The square root of 49 is always positive 7. Now, I know why some students have this misunderstanding, and I'm going to try to actually highlight it later in this lesson. But bottom line, square root of 49 is always positive 7. Square root of 49 is never negative 7. Okay? So that's one thing we need to remember about square roots. Secondly, it's very important that we now think about the following thing with regard to square roots of negative numbers. So here's what I want to say. You've probably been told in a previous math class that you can never find the square root of a negative number, something like square root of negative 9. Now let me be very clear. That is actually a correct statement, that you can't find square root of negative 9 if you understand the number system that you're working in. Usually when we're in a high school algebra math class, you're working with the set of real numbers. Remember the number line that we drew earlier on in this course when we were talking about absolute values? That number line represents the set of real numbers. You and I usually only label some of the whole numbers on that line, but the fact of the matter is that that line actually represents all real numbers. So things like 1/2, that's in there, negative 15/4 is in there, square root of 2, pi, they're all on the real number line somewhere. In fact, any number that can be represented as a decimal number is in the set of real numbers. So the number 7, I can write that as a decimal number, 0.5, or negative 3.729451, and even things like 0.333333 repeating, which is 1/3. And even square root of 2 and pi, which can be represented as infinite decimals without a really nice pattern, all of those numbers are inside the set of real numbers, which we normally represent with that number line. So if you're working in that set, then the square root of negative 9 makes no sense. You cannot find the square root of negative 9. However, today, I want to expand your knowledge just a bit by thinking about another set of numbers known as the complex numbers. Sometimes people call these the imaginary numbers. The complex numbers is the set of complex numbers is the set of numbers which can be written in the form a plus b times I, where a is just some real number, and b is also a real number, and I is a very special number, the square root of negative 1. That's right. I is the square root of a negative number. Now, I can just see some of you saying, no way, you can't have that thing. Well, that's what a lot of people actually said for a few hundred years when such a number was proposed. But I'm going to show you for the next several lessons how these can actually be used. So, let me be really clear. Something like the square root of negative 1, which I'm going to call I, is not a real number. And neither is square root of negative 9. That's also not a real number. So in the past, when you've seen these kinds of things and your teacher said that they don't exist, they were right, if they were talking about the real numbers. But if you and I are willing to think of this larger set of numbers called the complex numbers, then they actually exist. So that might feel a bit uncomfortable for now. Just bear with me as we walk through the rest of this lesson as we're dealing with square roots, okay? If you know what set you're working in, let's say the complex numbers versus the real numbers, if someone walks up to you and says, hey, what's the square root of negative 16? If they want you to give them a real number, you have to say, doesn't exist. But if they're okay with you making it into a complex number, then you can do that. And here's how you would. Square root of negative 16 is the same as square root of 16 times square root of negative 1, that just uses the rule we were talking about a few minutes ago. And the square root of 16 is just 4. We've known that. So now I have 4 times the square root of negative 1. And I'm saying that the square root of negative 1 equals I. And it always equals I. And therefore, my final answer is 4I. So as long as we work in the complex numbers, that would be my answer. Okay, so I've said enough about square roots for now. Let's talk about how we might use some square roots to solve quadratic equations. So let's look at the following example. I want us to solve x squared minus 36 equals 0. Now, if you remember our previous lesson, we actually saw how to solve this equation by factoring. Actually, this is an example of something I called a difference of two squares in the previous lesson. So let me suggest the following. Why don't you try factoring that equation quickly, and then we'll come back together. Okay, when you factored that, what did you get? Well, x squared minus 36 is a difference of two squares, so it factors as x minus 6 times x plus 6. And that means our equation, x squared minus 36 equals 0, can be rewritten as x minus 6 times x plus 6 equals 0. I split that into two equations, x minus 6 equals 0 and x plus 6 equals 0. And that means that my two solutions are x equals 6 and x equals negative 6. Now, I'd like to show you how to solve the exact same equation, but this time, instead of factoring, I want us to use square roots. One of the most important things about mathematics that we need to remember is that there's never anything wrong with knowing how to solve the same problem two different ways. Sometimes one way will be better than the other, but it's always good to have alternate ways of coming up with the same solution. So let me now show you how to solve this equation using square roots instead of factoring. First, I'm actually going to break one of the rules that I shared with you in the previous lesson. So don't kill me over this, but I'm actually going to start with that equation, x squared minus 36 equals 0, and I'm going to move the 36 over to the right-hand side by adding 36 to both sides. That gives me x squared equals 36. In the previous lesson, I kept telling you to move everything to the left side, move everything to the left side. And that usually does help. But in this special case, moving the 36 to the right is actually helpful. Now, x squared equals 36 is an equation where both sides are perfect squares. And that means I can take the square root of both sides. But there's a fact that some folks miss here, and that is that the square root of x squared might be x, or it might be negative x, depending on whether x is positive or negative to begin with. And so that means that when I want to go from x squared equals 36 to a new equation that uses square roots, I have to write the following. Square root of x squared equals plus or minus square root of 36. And this is exactly where some students fall into believing that the square root of 36 might be 6 or it might be negative 6. That is not what we're saying here. It's always the case that square root of 36 is 6. But when I want to simplify an equation like x squared equals 36 by taking square roots, then I have to insert this plus or minus. And that's why that plus or minus comes up. Not because the square root itself might be positive or negative. Okay, so let's finish this problem. I had x squared equals 36. I take the square root of both sides, and in doing so, the left-hand side becomes x, and I say that that's equal to plus or minus square root of 36, which is 6. And so that means I'm really writing two equations into one, namely x equals 6 or x equals negative 6. That's how I interpret the plus or minus. And guess what? That was exactly the answer we got just a few minutes ago with factoring using differences of two squares. Fabulous. So we get the same answer using two totally different methods. All right, let's try solving another equation using some square roots, and I'm going to suggest you try it first. Here's the equation. Solve x squared minus 144 equals 0. Okay, let's follow the same steps that we just followed in the previous example. X squared minus 144 equals 0. Adding 144 to both sides gives me x squared equals 144. I now take the square root of both sides, and I'll have square root of x squared equals the plus or minus square root of 144. And when I simplify that a bit, I'm going to have x equals plus or minus 12, because 12 squared equals 144. So the two solutions of this original equation are x equals 12 and x equals negative 12. Did you get those answers? If you did, you're in great shape. Now we could check those quickly just by plugging them into the original equation. Let's do that really quickly. The original equation was x squared minus 144 equals 0. Plugging in a 12 gives me 12 squared minus 144 equals 0. That's 144 minus 144, and that does equal 0. And so that one works out. So x equals 12 is definitely a solution. Let's try the negative 12. I'm going to plug negative 12 in for x, and now I see that the negative 12 is being squared. And when I do that, negative 12 squared is negative 12 times negative 12, which is positive 144. So I have 144 minus 144, which equals 0. So that equation is also true. And therefore, x equals negative 12, along with x equals 12, is a solution. Now, what have you noticed about both of the problems that we've started with? So there's something actually very special about the two examples I've just done, which gives me a hint that I can attack them with square roots. Well, you may or may not have seen it, so let me point it out to you. Both examples of the equations I just showed you were missing the x term. Did you notice that there was an x squared term and there was a constant, a 144 for example, but there was no x to the first term inside the equation that we started with? We could say it a different way. We only had perfect square terms in the equations we started with. Something like an x squared, which is a perfect square, and 144, which is 12 squared. So making that observation is very important if we want to use this tool. Using the tool of square roots to solve an equation works best when all the terms in the equation look like perfect squares. Now, it doesn't mean it can only handle those equations, but those are the equations that are best handled by using square roots. Okay, let's try a few more examples though where it may not be completely obvious that the square roots are going to be helpful, but let's try a few to show you how the square root tool can really help. Here's an example. Solve x squared minus 44 equals 20. Okay, what would you do here? Well, the first thing I'm going to notice, although it's a bit more complicated looking, is that there's still no x to the first term in this equation. That's a hint that I'm going to try square roots. Now you might be saying to me, yeah, but 44 is not a perfect square, and neither is 20. That's true. But let's do a little manipulating to the equation. Let's kind of add and subtract some things and see if perfect squares sort of pop up. The first thing I would suggest we do is add the 44 to both sides of the equation. And when you do that, you're going to have x squared on the left equals 44 plus 20, or x squared equals 64. That 64 is a perfect square. The 44 and the 20 were trying to throw us off. But the 64 is a nice perfect square. And if I go with x squared equals 64 and do this square root tool with both sides, I'll have the following. I'll have square root of x squared equals plus or minus square root of 64. Remember, the plus or minus is just coming in because we don't know if the x itself is going to be positive or negative after we've done all this work. So I have square root of x squared equals plus or minus square root of 64, and that's the same as x equals plus or minus 8. And once I've done that, I know that the solutions are x equals 8 and x equals negative 8. Now, I could check both of these by plugging them into the original equation, x squared minus 44 equals 20, just to make sure we've done the problem right. I'm going to leave that to you. We've done a lot of that kind of checking in the past. I'll leave it to you. It's an important step. But let's keep moving at this point to some other examples so I can show you the variety that comes up with this square root tool. Now, let's do another example of solving a quadratic equation using square roots. Here's one. Solve x minus 3 squared minus 49 equals 0. Now, I have to be honest, this problem actually is very interesting to me because there really is an x to the first term in the problem, but it's hidden from us. Let me show you really quickly what I mean. If you take the left-hand side of that equation and you multiply it out, you actually get the following. X minus 3 squared minus 49 equals x minus 3 times x minus 3 minus 49, which is x squared minus 6x plus 9 minus 49, which is x squared minus 6x minus 40. That means the original equation could have been written as x squared minus 6x minus 40 equals 0. Hey, I see an x to the first term right in the middle of that left-hand side. You see that 6x? So it turns out that there was an x to the first term there, but we didn't see it in the original version of the equation, and that's not a problem. The point is that the way the original equation is written makes everything look like a perfect square. That original equation really looks like it's got a whole bunch of perfect squares in it. So I want to go back now to that original version and use the square root tool. All right? Why don't you try it first, see if you can solve that equation using square roots, and we'll check back with each other in a moment. Okay, so we're trying to solve x minus 3 squared minus 49 equals 0. Here's how it works. We're going to add the 49 to the other side, and we'll have x minus 3 squared equals 49. And now we do the square root tool. We take the square root of x minus 3 squared on the left, and that's equal to plus or minus square root of 49 on the right. Now that square root of the x minus 3 squared is just going to leave me an x minus 3 on the left, and the right-hand side becomes plus or minus 7. And now you and I need to be very careful about how we split this into two equations, because they're going to become the following. X minus 3 is going to equal 7, or the x minus 3 equals negative 7. That's how we split up that plus or minus so that we get the right two equations. So I have x minus 3 equals 7, or x minus 3 equals negative 7. And if I just add those 3's to the right-hand side, I'm going to have x equals 7 plus 3, or x equals negative 7 plus 3. And that means my two equations are, my two solutions are x equals 10 or x equals negative 4. Now, this is an example where the two solutions don't just look like the positive and negative of one another. So we should definitely check to make sure we did this problem correctly by plugging in these two numbers into the original equation just to make sure they make the equation true. So here we go. Let's try plugging 10 into the original equation. X minus 3 squared minus 49 equals 0 becomes 10 minus 3 squared minus 49 equals 0. And by order of operations, I've got to do the 10 minus 3 first because it's inside the parentheses. So I'll have 7 squared minus 49 equals 0. Now I do the exponentiation, so I have 49 minus 49 equals 0, or 0 equals 0. 0 does equal 0, so 10 is a solution. Let's try the other one. I have negative 4 minus 3 squared minus 49 equals 0. Remember, I'm plugging negative 4 into the original equation. Now I do what's inside the parentheses first. Negative 4 minus 3 is negative 7. So I have negative 7 squared minus 49 equals 0. Negative 7 squared is the same as negative 7 times negative 7. And that'll be positive 49. When you multiply two negative numbers together, you get a positive one back. And that means you're going to have 49 minus 49, which equals 0, or 0 equals 0. That's also true. And therefore, we know that our two numbers, x equals 10 and x equals negative 4, really are solutions of the original equation. Okay, so now I actually have to be honest with you and let you know that not everything has to look like a perfect square in order to use the square root tool. So let me show you the following example, which is just a little bit different from the ones I've just done. Let's solve x squared minus 63 equals 0. Now, I know the x squared is a perfect square because it's x times x. But 63 is definitely not a perfect square. But that's not a problem. We can actually keep moving forward with the square root tool if we'd like. The key is that we're missing an x to the first term. And that's the real hint that the square root tool is the right thing to do. So, x squared minus 63 equals 0. I'm going to add 63 to both sides, giving me x squared equals 63. I just take the square root of both sides, and I'll have square root of x squared equals plus or minus square root of 63. And that's the same as x equals plus or minus square root of 63. And now you look at me and you say, yeah, but 63 is not a perfect square. What am I supposed to do now? Well, let's just simplify square root of 63 as much as we can. 63 is the same as 9 times 7. So my equation becomes x equals plus or minus square root of 9 times 7, which is the same as saying x equals plus or minus square root of 9 times square root of 7. Remember, I can split across a product when I'm doing square roots. And that simplifies to x equals plus or minus 3 square roots of 7, or 3 times square root of 7. And that means my two solutions are sitting in front of me. X equals positive 3 times the square root of 7, and x equals negative 3 times the square root of 7 when I split up that plus or minus sign. Okay, I want to look at one more example which is going to involve some of those complex numbers. I know some of you are probably feeling a bit uncomfortable right now with those, so let's do another example with the hope that you feel more comfortable with them once we're done. Here's the example. I want to solve x squared plus 48 equals 0. And since I don't see an x to the first term in the equation, I'm going to try using the square root tool. So I start with x squared plus 48 equals 0, and I now subtract 48 from both sides, leaving me with x squared equals negative 48. And now I can hear some of you telling me, hey, there's no number squared which can equal negative 48. And you would be right if you meant that there was no real number that you could square to give me a negative 48. That would be perfectly correct. So if you or a teacher said, would there be any solutions in the real numbers? The answer is that there's no solution at all. And often, in a lot of algebra classes, that's where we would stop. We would simply say that there were no solutions to the original equation. However, if we open up the set of numbers that we're allowing to be part of the solution, and we start thinking about complex numbers, then we know about the number I, which is the square root of negative 1, and that will help us find a solution. So let me use that now to finish the problem. I was at the point of x squared equals negative 48. I take the square root of both sides. So I have square root of x squared equals plus or minus square root of negative 48. The left-hand side becomes x. So I have x equals plus or minus square root of negative 48. Now, split negative 48 up as 16 times 3 times negative 1. Think about it for a minute. 16 times 3 times negative 1 is negative 48. And now I can split that up into the product of 3 square roots. And I'll have x equals plus or minus square root of 16 times square root of 3 times square root of negative 1. Now, square root of 16 is 4. Square root of negative 1, I'm just going to call this thing I. And that means I'm down to x equals plus or minus 4i times the square root of 3. Now, those are not real number solutions. I know they're not, but they are complex number solutions. They are x equals 4i times the square root of 3 and x equals negative 4i times the square root of 3. And those would be answers as long as we allow complex numbers to come into the game. Now, you might be asking, what if my teacher or a standardized test had asked me if there were solutions to that original equation? How would I answer? Well, to be honest with you, most of the time they're probably asking you for a real number solution, and that means that your answer would need to be there's no solution. But you need to be sure. If they're okay with complex number solutions, then you'd need to answer that there are two solutions, 4i times the square root of 3 and negative 4i times the square root of 3. Well, that's all the time we have for today's lesson, but let me say this before we end. I introduced today the complex numbers, and you might be thinking that these are just a waste of time. If you think that, then you'd be wrong. Complex numbers are used throughout calculus, differential equations, and a whole lot of other math courses. Engineers use them, physicists use them, lots of people use complex numbers. So you don't want to ignore them too quickly. They often come in very handy, and they even play a key role in the development of beautiful mathematical objects known as fractals, with which some of you might be familiar. Next time, we're going to talk about even another tool for solving quadratic equations, which is called completing the square. It's really helpful in finding the vertex of a parabola. That's the graph of a quadratic function. We've seen those in the past. And when you combine this tool of completing the square with the tool of square roots that we just discussed, it's extremely powerful. So I look forward to talking about completing the square in our next lesson.